Raman Spectra Introduction. It is a special type of spectroscopy which deals not with the absorption of electrons but deals with the scattering of light by the molecules. It is observed that when a substance which may be gaseous, liquid, or even solid is irradiated with monochromatic light of a definite frequency mu, a small fraction of the light is scattered. Rayleigh found that if the scattered light is observed at right angles to the direction of the incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, or solid, is irradiated with monochromatic light of a definite frequency mu, the light scattered at right angles to the incident light contained lines not only of the incident frequency but also of lower frequency and sometimes of higher frequency as well. The lines with lower frequency are called Stokes lines, whereas lines with higher frequency are called anti-Stokes line. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If mu I is the frequency of the incident light and mu s that of a particular scattered line, the difference delta mu is equal to mu I minus mu s is called Raman frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristics of that substance. The various observations thus made by Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be represented as shown in figure. Explanation for observing Rayleigh line and Raman line. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collisions means that the colliding particles will return with the same energy. Thus, the scattered photons has the same frequency as that of the incident photon. This explains Rayleigh scattering or Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good, that is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and hence lower frequency than that of the incident photon. This explains the occurrence of Stokes lines. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photons has the higher energy and these higher frequency than that of the incident light. This explains the occurrence of anti-Stokes line. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes lines. Thus, a part of the energy of the incident photon remains absorbed by the molecule, so that molecule has higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level, thus more energy is emitted than absorbed. This explains the occurrence of anti-Stokes line. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown in figure. Levels have been shown equally spaced just for the sake of convenience. Polarizability of molecules and Raman spectra. The Raman effect arises on account of the polarization, distortion of the electron cloud of the scattering molecules that is caused by the electric vector of the electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field E and the nature of the molecule. We write mu is equal to alpha E, where the quantity alpha depends upon the nature of the molecules and is called polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of atoms or spherically symmetrical molecules, spherical rotors such as CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, non-spherical rotors, the polarizability depends upon the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond that when it is applied perpendicular to it, and we write alpha parallel is greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Types of molecules showing rotational Raman spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule is give a rotational Raman spectra is that the polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon his orientation of the molecule with respect to the direction of the electric field. Hence, all diatomic molecules, linear molecules, and non-spherical molecules give Raman spectra, that is, they are rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6, etc. do not give rotational Raman spectrum, that is, they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is the sum of two parts. Equilibrium polarizability alpha node, that is the polarizability when the atoms of the molecules are in their equilibrium positions. Second, sum of the polarizabilities of the molecule due to the various rotational and vibrational motions, each term depending upon the frequency of rotation or vibration. Thus, alpha is equal to alpha node plus summation of curl alpha n divided by curly r into Rn cos 2 pi mu n t, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atoms involved. Further, the electric vector of the electromagnetic radiation varies with the time in a sinusoidal manner as E is equal to E naught cos 2 pi mu naught t. Substituting values of alpha and E from equation 2 and 3 in equation 1, we get mu is equal to E naught alpha naught cos 2 pi mu naught t plus summation of curly alpha n divided by curly r into Rn cos 2 pi mu n t cos 2 pi mu naught t, that is equal to E naught alpha naught cos 2 pi mu naught t plus 1 by 2 E naught summation of curly alpha n divided by curly r into Rn into cos 2 pi into mu naught minus mu n into t plus cos 2 pi into mu naught plus mu n into t. This expression consists of three terms. The first term has the frequency of the incident radiation and represents Rayleigh scattering. The second term contains mu naught minus mu n and represents Stokes lines, whereas the third terms contain mu naught plus mu n and represents anti-Stokes line. Quantum theory of pure rotational Raman spectrum of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are delta J is equal to 0 in plus minus 2. The selection rule delta J is equal to 0 corresponds to Rayleigh scattering, whereas selection rule delta J is equal to plus minus 2 gives rise to Raman lines as explained below. We know that the energy of a rotational level in terms of wave number with quantum number J is given by mu bar is equal to Bj into J plus 1. When a transition takes place from a lower rotational level with the quantum number J to a higher rotational level with quantum number J dash, the energy absorbed in terms of wave number will be delta mu bar is equal to bj dash into j dash plus 1 minus bj into j plus 1. For the selection rule, delta j is equal to plus 2, that is j dash minus j is equal to 2 or j dash is equal to j plus 2. We get delta mu node bar is equal to b into j plus 2 into j plus 3 minus bj into j plus 1 is equal to b 4j plus 6, where j is equal to 0, 1, 2, 3. Again, for the selection rule, delta j is equal to minus 2, that is j dash minus 1 is equal to minus 2 or j is equal to j dash plus 2. We get delta mu bar is equal to b j dash into j dash plus 1 minus b into j dash plus 2 into j dash plus 3, that is equal to minus b 4j dash plus 6, where j dash is equal to 0, 1, 2, 3. Combining the results of equation 3 and 4, the wave number of the lines obtained in the Raman spectrum will be given by mu bar is equal to mu I bar plus minus delta mu bar, or mu bar is equal to mu bar I plus minus b into 4j plus 6, where j is equal to 0, 1, 2, 3. Here mu I bar represent the wave number of the Rayleigh line, plus sign gives lines with higher wave numbers called anti-Stokes lines, and minus sign gives lines with lower wave number called Stokes lines. From equation 5, it may be seen that for j is equal to 0, mu bar is equal to mu I bar plus minus 6b, that is the first Stokes and anti-Stokes line will be at a separation 6b from the Rayleigh line. Further, putting j is equal to 1, 2, 3, the separation between any two adjacent Stokes lines or anti-Stokes lines will be 4b. Thus, the pure rotational Raman spectrum expected for a diatomic molecules may be represented as is shown in figure. Intensities of lines of the pure rotational Raman spectrum. As explained earlier, the intensities of the line depend upon the population of initial level from where the molecules are excited or de-excited to the final level. Since the population of rotational energy levels is shown in figure, therefore the intensities of the Stokes and anti-Stokes lines vary in a simple manner. Application of pure rotational Raman spectrum. From the pure rotational Raman spectra, nothing the separation between the lines, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecules can be calculated as explained earlier. Quantum theory of rotational vibrational Raman spectra of diatomic molecules. For large molecules, the lines obtained due to rotational transitions are so weak that they are beyond resolution. Hence, we have pure vibrational Raman spectra for which the selection rules are same as for pure vibrational spectra discussed earlier, that is delta mu is equal to plus minus 1 and plus minus 2 and so on. However, in case of diatomic gaseous molecules, the resolution of rotational line structure is sufficient and can be studied. Thus, diatomic gaseous molecules give rotational vibrational Raman spectra, which can be explained as follows. The selection rule for the transitions are delta mu is equal to plus minus 1, delta j is equal to 0, plus minus 2. However, at room temperature, as most of the molecules are in the lowest vibrational level, that is mu is equal to 0, therefore the significant vibrational transition is from mu is equal to 0 to mu is equal to 1 called fundamental vibrational transitions. Restricting ourselves to this vibrational transition only, the result obtained are as follows. For delta j is equal to 0, delta mu bar is equal to omega e into 1 minus 2xe called q branch. For delta j is equal to plus 2, delta mu bar is equal to omega e into 1 minus 2xe plus b into 4j plus 6 called s branch. Delta j is equal to minus 2, delta mu bar is equal to omega e into 1 minus 2xe minus b into 4j dash plus 6 called q branch. Representing the values for q, s and o branches by delta mu q bar, delta mu s bar and delta mu o bar respectively, and the wave number of the exciting radiation by Vi bar. The wave number of the Stokes lines will be as follows. Mu q bar is equal to mu I bar minus delta mu q bar, mu s bar is equal to mu I bar minus delta mu s bar. delta mu O bar is equal to mu I bar minus delta mu O bar. We have considered the case for delta mu is equal to plus 1, which represents Stokes lines. The anti-Stokes lines are those for which delta mu is equal to minus 1. They are usually weak because very few molecules are in the excited vibrational state initially. The rotational transitions accompanying the vibrational transition from mu is equal to 0 to 1 and the rotational vibration Raman spectrum obtained may be represented as shown in figure. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. First one, since Raman frequencies are independent of the frequency of the incident radiation, hence by suitably adjusting the frequency of the incident radiation, Raman spectra can be obtained in the visible spectrum range where they can be easily observed rather than the more difficult infrared range. Second, Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Third, Raman spectra can be obtained not only for gases but even for liquids and solids, whereas infrared spectra for liquids and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of a large number of compounds have been determined by Raman spectroscopy. However, infrared method still continues to remain popular. Experimental arrangement for Raman spectra. The fraction of the light scattered is so low that normally very weak Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of wavelength 4358 angstrom, that is 435.8 nanometer. However, with the development of lasers, which are very powerful sources of monochromatic radiation, Raman spectroscopy has been greatly revolutionized.